This topic moves from concepts to practice. We focus on how green roof performance simulation is used in planning, which tools fit which questions, how to build defensible workflows, and how to communicate results. The core idea is that tools are not an end in themselves. A simulation is valuable only if it supports a decision, selecting sites, sizing systems, comparing scenarios, or demonstrating compliance. We will keep slide text keyword driven and use the narration to explain what each step means and where people typically go wrong. We will focus on practices that reduce rework, clear questions, explicit assumptions, and outputs that link to planning decisions like prioritization, sizing, and compliance narratives. You will also see how to avoid the common trap of mixing metrics from different spatial and temporal scales without stating the mismatch. The agenda follows a planning logic. First, we place simulation in the planning cycle from early screening to operation. Then we describe the data you need at planning scale, and the main tool families: building energy simulation, stormwater and drainage models, microclimate models, and GIS-based scenario mapping. Next, we cover scenario design and choice of metrics, and we discuss standards and checklists that keep projects defensible. We end with implementation constraints, monitoring feedback loops, and 2 best practice examples from the evidence pack. As we go, notice how each tool family has a sweet spot and a failure mode. Your job is to stay inside the sweet spot and document the failure mode. Learning objectives for this topic emphasize tool choice and process quality. You should be able to locate simulation in the planning cycle, select tools that match the planning question and available data, and define transparent assumptions. You should be able to build a scenario set and compare options using metrics that stakeholders understand. Finally, you should be able to communicate uncertainty honestly, because overconfident outputs are a common reason simulation work gets rejected in review or ignored in practice. In other words, you are learning how to run a workflow that a skeptical reviewer would accept, not how to generate pretty plots. In planning, simulation is used differently at each stage. In site screening, you use quick models and GIS to decide where green roofs are feasible and impactful. In concept alternatives, you compare design variants such as substrate depth, plant mix, and coverage targets. In design development, you size drainage, determine structural constraints, and run more detailed simulations. In permitting, you prepare evidence for stormwater, energy, or biodiversity requirements. In operation, monitoring data are used to update assumptions and check whether performance matches the promise. A useful rule is to start with the lowest complexity tool that can answer the question, then add complexity only if the decision requires it. Planning quality data is often coarse and uncertain, so you must be explicit about what you know and what you assume. Roof inventory data include area, slope, and structural load constraints. Climate inputs include typical weather as well as extremes that drive risk, such as heat waves and intense rainfall. For stormwater, planners often rely on local rainfall intensity duration frequency curves and design storms. For energy, archetype buildings with typical schedules are common. Context matters too. Shading, wind exposure, and urban heat island hotspots change the expected benefit of greening a specific roof. If you cannot get a parameter from tests or product data, record where the number came from and run a sensitivity range so the result is not held hostage by a guess. For rainfall, temporal resolution matters. Hourly rainfall can hide peaks that drive overflow, so select data that matches the design question. The tool landscape can be confusing because many tools overlap. Building energy simulation estimates changes in heating and cooling loads. Stormwater models estimate runoff volume, peak flow, and system overflow risks. Microclimate and CFD tools estimate outdoor thermal comfort and local air temperature patterns. GIS tools map roof suitability and support scenario-based portfolios. Multi-criteria decision tools combine metrics such as heat risk reduction, flooding reduction, biodiversity value, and equity. The key is to avoid treating all tools as equally credible for all questions. Each has a domain and a scale where it performs best. Keeping the tool map explicit also helps interdisciplinary teams. Engineers, planners, and ecologists can see who owns which metrics and what data they must provide. For building energy questions, a common practice is to use a whole building simulator such as Energy Plus with a green roof module. You start by defining the question: cooling load reduction, peak demand, or indoor comfort. Then you define roof layer properties, plant parameters, and weather data. Outputs typically include changes in annual loads and peak hour behavior. If you have a monitored building, calibration strengthens credibility. If you do not, sensitivity analysis is essential. Always report results as differences from a baseline roof and specify the time horizon, because a summer peak effect can look very different from an annual average. When calibration data are missing, be conservative. Emphasize relative differences between scenarios and avoid presenting absolute savings as guaranteed outcomes. A practical deliverable is a short assumption sheet that lists roof buildup, plant parameters, and weather file, so reviewers can see what you modeled without digging through input files. For stormwater questions, SWMM is widely used because it can represent both catchments and drainage networks. A planning model typically defines subcatchments, drainage connectivity, and low-impact development controls that represent green roof storage and release. Parameters include storage depth, conductivity, and drainage characteristics. Outputs include hydrographs, peak reduction, and overflow events. Good practice is to run both a design storm for sizing and continuous simulation for seasonal behavior. Calibration against runoff measurements, even from a small pilot roof, can greatly reduce the risk of overclaiming retention performance. For stormwater, always confirm how the model treats antecedent moisture, because dry versus wet initial conditions can dominate predicted retention. When planners talk about compliance, they often mean peak flow under a specified event. When they talk about resilience, they mean continuous performance across seasons, so run both and label them clearly. For microclimate and heat stress questions, tools such as EPD-Net simulate surface plant-air interactions at high spatial resolution. The strength of these tools is local detail, how airflow, shading, and surface properties interact around buildings. The risk is false precision. The input burden is high, and small errors in boundary conditions can produce large changes in local air temperature or comfort metrics. In planning contexts, use microclimate models to compare relative changes between scenarios and to identify hotspots, not to promise a specific temperature reduction to the second decimal place. For heat stress studies, pair model outputs with qualitative site knowledge, street canyon geometry, shading, and present results as comparative deltas, not as exact degrees everywhere. If a project cannot afford microclimate modeling, you can still use simpler heat metrics and focus EPD-Net only on a few representative hotspots. GIS-based roof suitability mapping is a planning workhorse. The basic workflow is to extract roofs, often using building footprints and, when available, litter-derived roof shapes. Then you apply constraints such as shading, heritage restrictions, access, and load limits. Next you add weights that reflect planning priorities: heat risk reduction, flood risk reduction, ecological connectivity, or social equity. The outputs are not a single answer but a portfolio: priority maps, candidate project lists, and adoption scenarios that can be revisited as budgets and policies change. Portfolio outputs are especially useful when you include equity layers, so that benefits are not only maximized but also distributed according to vulnerability. If litter is unavailable, you can still build a useful roof inventory from building footprints and typical roof archetypes, but you must be explicit about the uncertainty this introduces into city-level benefit estimates. Scenario design is where you turn tools into policy-relevant evidence. Start with a baseline that reflects current roofs and current climate. Define interventions as a set of alternatives: coverage rates, substrate depths, irrigation strategies, and maintenance assumptions. Include extremes, such as heat waves or high-intensity storms, because those events drive risk. Choose metrics that match the decision: kilowatt hours, peak demand, cubic meters of runoff avoided, time to peak delay, or simple risk indices. When costs are part of the decision, present co-benefits and avoided damages, but keep the uncertainty explicit and avoid pretending you can monetize everything with high confidence. Make sure each scenario varies only the levers you intend to test. Otherwise you cannot explain which change caused which outcome. Standards and checklists keep design and simulation aligned with real-world constraints. Green roof guidelines address growing media testing, drainage layer behavior, root resistance, and maintenance requirements. Planning teams should also check local fire safety, wind uplift, and waterproofing details, because these constraints can override the optimal, simulated configuration. From a simulation perspective, Standards help you choose realistic parameter ranges and document them. This is crucial for auditability. Reviewers trust a parameter value more when it is tied to a recognized guideline or test method rather than a guess. Guidelines also reduce liability. They show that your parameter choices were aligned with accepted practice rather than invented for a single project. When guidelines conflict with local codes win. Record the conflict and adjust the design question rather than ignoring the constraint. Communicating results is as important as running the model. Decision makers need clear visuals and a short explanation of assumptions, not a thick report of raw outputs. Use graphics that compare scenarios, show ranges and sensitivity, and highlight peak conditions as well as averages. Explicitly state what the model does not include, such as tenant behavior changes or long-term vegetation shifts, unless you modeled them. Link metrics to stakeholder goals, heat risk, flood risk, energy costs, biodiversity commitments, or regulatory compliance. A good communication package makes it easy for a reader to reproduce the logic of the analysis. A strong communication package usually fits on one page: scenario definition, key metrics, uncertainty statement, and the single recommendation that follows from the evidence. Implementation constraints are where many planning proposals fail. Structural load limits can eliminate intensive designs on existing buildings. Roof detailing and leak risk matter, especially around penetrations and edges. Safe access for maintenance is often neglected, yet maintenance strongly affects long-term performance. Irrigation can be a requirement for thermal benefits in dry climates but may be infeasible due to water scarcity or policy. Funding and governance matter too. Incentives, mandates, and responsibility for maintenance determine whether a plan becomes a built project or a shelf report. Treat constraints as inputs, not afterthoughts. The easiest way to waste weeks is to optimize a roof design that the structure cannot carry or that maintenance cannot support. For retrofit projects, include a quick structural screening step early. It is better to reject infeasible roofs fast than to produce perfect simulations for roofs that cannot be built. Monitoring closes the loop. A minimal monitoring plan might track soil moisture, surface temperature, and runoff at the drain outlet, paired with basic maintenance logs. These data can be used to update model parameters and detect performance drift, such as reduced retention due to clogged drainage or reduced evapotranspiration due to plant loss. The point is not to turn every roof into a laboratory. It is to collect enough evidence to improve future assumptions and to refine policy targets. In professional practice, even simple monitoring can protect a city from repeating the same modeling mistakes across multiple projects. Even a small monitoring sample across a city can improve future planning models, because it anchors key parameters like retention capacity and thermal lag in local conditions. Best practices in the evidence pack illustrate how planning, design, and evaluation connect. The greenest of the green block in Helsinki is presented as a research-linked development that explores rooftop green space functionality and resident experience, using co-design and stakeholder engagement. The Oh Boy project in Malmö uses both extensive and semi-intensive roof areas, with varied substrate depths and strong biodiversity intent. Both cases underline a practical lesson: multifunctional roofs require multifunction metrics. If you only model stormwater, you will miss the social and ecological dimensions that often motivate adoption. Both cases also show that success is multidimensional. Resident use, biodiversity goals, and water management outcomes can conflict unless you define priorities early. In Malmö's Oh Boy case, the varied substrate depths and wetland roof concept illustrate how design can intentionally create multiple habitat conditions on the same roof. Common pitfalls are predictable and avoidable. Using the wrong climate file or the wrong temporal resolution for rainfall can invalidate results. Unrealistic substrate parameters, especially hydraulic conductivity and moisture capacity, can exaggerate retention or cooling. Lack of calibration leads to fragile conclusions. Overclaiming precision can damage trust. It is better to report ranges and compare scenarios. Ignoring maintenance is a silent failure mode, because performance degrades over time when drainage clogs, plants die back, or irrigation changes. A rigorous workflow treats these pitfalls as checklist items, not as afterthoughts. When a pitfall is detected, the fix is usually procedural. Change the workflow, not just the parameter, by adding a check, a data source, or a required sensitivity run. The toolchain example shows how tools can be combined without turning into a mess. Start with GIS roof inventory to define what is feasible. Feed candidate roofs into an energy model to estimate building impacts and into a hydrology model to estimate runoff benefits. Add microclimate modeling only where local heat stress is a priority and the urban form justifies detailed analysis. Then integrate outputs into a simple decision dashboard that compares scenarios with ranges and sensitivity. The last step is iteration. Update the scenario set based on stakeholder feedback, budgets, and policy constraints. The integration step should end with a traceable decision table that links each metric to a stakeholder goal and indicates whether the evidence is strong, moderate, or conditional. The moment you cannot explain a model output in plain language, you have lost the thread. Go back to inputs, processes, and sensitivity until the story matches the physics. To summarize, tools serve decisions, not aesthetics. Data quality drives credibility, so document sources and assumptions. Use scenario sets and metrics that match the planning question, and communicate uncertainty explicitly. Combine models only when it adds value, otherwise keep it simple. Close the loop with monitoring and maintenance, because performance claims without feedback are marketing, not planning. If you remember only one thing, a transparent workflow beats an opaque, black box result, even if the black box looks more sophisticated. This slide begins the reference list for the planning tools and practices topic. The reference list includes both peer-reviewed studies and authoritative tool documentation. When your workflow relies on a software capability, cite the official manual or documentation for that software. When your workflow relies on a rule of thumb, try to replace it with a guideline or a tested parameter range. These habits reduce legal risk and increase the chance that your outputs survive external review. Use the references as a verification checklist. Each key claim in your report should be traceable to an authoritative document or a peer-reviewed study. This slide continues the references. A final reminder is that planning simulation is an argument, not a number. Your argument is only as strong as your assumptions, your data, and your transparency about limitations. If you cannot verify a source, do not use it. If you cannot justify an input, bracket it and test sensitivity. This is how simulation becomes a trustworthy planning practice rather than a decorative technical exercise. In practice, this means writing down your data sources, your model versions, and your parameter sets, so someone else can reproduce the run and reach the same conclusion.